Assalamualaikum my students, Al Sir here. Welcome you again to our another unit that is very special unit in our syllabus, and it is continuity. We have today to define the continuity of a function f of x at some point x is equal to a in its domain. So now, without wasting our time, we are directly going to this definition. First we will analyze its definition on graph. We know that if we have this function f of x, graphically this function represents a curve. And if this f of x is defined in some interval, we say this c to d. This interval can be anything. It will be either open, closed, or this semi-open, semi-closed. But now here we will define this f of x on this open interval. In this open interval. Now we know that this function represents now curve. So if we draw the curve of this function in this interval CD, if we get the graph in such a way that when we draw the graph, the pen is not getting lifted at any point over this interval CD, then we will say that this function f of x is continuous in this interval CD. But if we have a point a belongs to this CD, if we have some point a belongs to this CD where this function is defined, and when we are drawing the graph of this curve f of x, at this point a, we are lifting our pen. For this is our a point, we are lifting here our pen. Then we will say that this function is not continuous at this point a belongs c comma d. So it is the easy definition for this continuity of a function at some point. We will say the function is continuous at a belongs to cd if and only if we are not lifting our pen when we are drawing our graph. We are not lifting our pen at that point. Now we will write its definition. Right, a function f of x is said to be continuous and we are talking about interval. So we will say function is continuous in an interval if and only if we can draw the graph. We can draw the graph of our function over the interval without lifting our pen. For example, if we have this y axis and this our x axis, and if we have a function f of x like this, you check we have drawn the graph of this function without lifting our pen at any point. So this is the continuous function or the domain from this point to this point. This is continuous. Similarly, if we draw another like this, again from this point to this point, so in this interval we are not lifting our pen, so this is also the continuous function or this interval from this point to this point. So this is the graphical definition of this continuity. Over the interval, and we can now easily define it at point. We know now at point x is equal to a, the function is continuous if at that point we are not lifting our pen. So here similarly you can now draw some examples of discontinuity function at x is equal to a. If we have this x-axis and this is our y-axis and this is our point A. If at this point we have a function like this and then it gets like, so here it gets jumped, so this is the discontinuous function at this x is equal to A. Similarly you can draw some more examples. It is easy now. Now we are going to its original definition that you have to take in consideration. If we have the function f of x and it is continuous and x is equal to a, that means if this is x, this point is my x is equal to a, sorry, if this is my x-axis, this is my y-axis, and this is my function which is continuous at this point here, x is equal to a, x is equal to a. Now how we can write this definition? We have already written this graphical definition. Now we will write this definition like this. If we can say that this function is continuous, you can draw its definition from this very graph also. Now you check here. We can say that this function is continuous at this x is equal to a. If and only if when we put the value of x is equal to a in this function f of x, so that will be f of a. If it is defined, or if it exists, then we can say then it is possible for us the function is continuous. Otherwise, if this f of a, if the value of the function at this point a is not defined, does not exist, then we cannot say that the function is continuous here. Why? Because we don't know the value of the function, whether the function, how can we draw at that time the graph of the function? Well, we don't know whether this x is, whether at this x is equal to a, the function is defined or not. How can we draw then the graph of this function? We cannot draw the graph of that function. So if it is not exists here at f is equal to a, then it may have here jump, or it may have this hole or something else. So we cannot say then it is continuous. So first condition, we will write this definition now like this. A function f of x is continuous at x is equal to a. At this point, this function is continuous if and only if. First condition. So definition, first one we have defined it graphically. Now we will draw the definitions of this continuity by this graph. So here, function is continuous at is equal to a if and only if, first one, f of x is defined at x is equal to a, that is f of a exists. This f of a exists here. Then we can say that this f of a is we can say that this f of x is continuous. We can check after that but first condition, first requirement is this f of a must exist at that point. So second condition is yes. If we, now you have to make here, if we will give the values of this x very near to this a, that means if we will approach, if we turn this x to a here, the values that are left from left side and from right side, if at that time the function is getting turned towards this f of a, for example this is my f of a here, this point, so if this is f of a, this is a, if at this point when we are turning this x to a, when we are approaching the values of x very near to a, at that time, if the function is getting very near to a, then we can say that the function is continuous. So how we can we are making this requirement? It is because when this x tends to a, that means this is getting close to this point. If the function is not getting at that time close to this point, this f of a is not getting close to this f of a, then the graph of this function must not have like this, because when it is not approaching to f of a, then it will go here either upside or downside, then here it will not meet at this point. So we cannot we will definitely get here break, or we will get here this gap, and at that time the function is not continuous. So the second requirement is that limit x tends to a, f of x must exist, because ये exist होना चाहिए, and must be equal to f of what a, ये f of a की तरफ हमें आना चाहिए, वही अप्रोच होना चाहिए. So that is, we know that this limit x tends to f of x exists only if this left hand limit at x is equal to a and right hand limit x is equal to a, they are equal and are approaching to the same value. So that means we can say that if this limit x tends to a negative f of x, that is equal to limit x tends to a positive f of x is equal to this f of this a, f of a. Now you check here whether this condition is actually assurance of continuity or not. You see here, beta, if this limit x tends to a, f of x, if it tends to another value that is not equal to f of a, or if we take that L, we know that f of a is like at this point, if this limit, if the values that are close to this, if we will give the values of the function close to this a, and at that time if we are getting another point, that means L, for example the L is here or here, if we are getting that point at L here, and you check here at this point, we have to come down to this, and then we have to go opposite. So here I am getting the, if this f of x at that time is approached to this point, then we are definitely getting this gap or this hole, then this function is not continuous. So this is the assurance for a function to be continuous. So this limit from the left side and the right side, they must approach the function towards the f of a, otherwise it is not continuous. So this is my requirement for continuous of a function. What is a? First of all, f(x) should be defined at that point. So another one is the limit of the function at that point must exist and must be equal to f of this a. Then we can say that the function is continuous. Now we are going to give it another definition. It is our positive definition that this positive f of a must exist. Second one is limit x tends to a, negative f of x is equal to limit x tends to a, positive f of x, that must be equal to this f of a. Then we are saying this is our positive definition, then we are saying the function is continuous. Now here this x tends to a, we are saying that limit x tends to a f of x, if this is equal to f of a, then the function is continuous. Now you check here, limit x tends to a, that means we have already given its meaning. It means this x minus a less than delta. We have already given its meaning that when we are telling x equal to a, that means this x minus a less than delta, where this delta is very small. So it further implies this x belongs to a minus delta, a plus delta. I have already given this thing in our previous lecture, the previous class, that was about limits. So here again, if we have this condition, then at that time if the function f of x, when this condition prevails, if the function at that time f of is approaching to is tending to this f of a, that means if the function f of x just same as this f of x minus this f of a is less than, we can say epsilon now, but this epsilon and delta, we make them relate to each other. Why? Because we have to define the continuity, and this delta and continuity at this extends to a, so these extends to a, this must be related to each other. So this delta, we will say that it is dependent on this epsilon. Otherwise we can put here some other x belongs to this open interval, we can put here x belongs to a minus 2, a minus 3, a minus 4, so we can make so many open sets here where this x belongs to. But when we will make this delta dependent on this epsilon, at that time we must have finite conditions for making this open interval. So here we will make this, if this thing happens x tends to a, that means this, at that time if we have this x tends to a like this, epsilon there, then we say that the function is continuous. Same to this condition. So we can write the definition like this also. If x tends to a at that time, or if x minus a less than delta, or if x belongs to this a minus epsilon, at that time if the function, if the distance between the function at the value and the value f of a is less than epsilon, then we say that the function is continuous. This is our second definition. All the definition is I have connected with each other. So here third one is third, a function, you have to write down all the definitions. A function f of x is said to be continuous at x is equal to a if and only if there exists epsilon positive such that f of x minus f of a less than this epsilon for all x minus a less than delta, but we have confined this delta dependent on epsilon. I have already told you why, because by making this condition, it will give us the relation between this to r for all x belongs to this, or I can write both these to this if and only if this f of x belongs to, here you check this, I can write this condition also as this f of a plus epsilon, or f of a minus epsilon, comma f of a plus epsilon. That means if and only if the values of the function are from this f of a minus epsilon to f of a plus epsilon for all when this x belongs to a plus this del, a minus del, a plus del. This is our definition, another definition of this continuity of a function. That means, what is that? If f of x belongs to this open interval, for all x belongs to this open interval, then we say that the function is continuous. So this was all about the continuity of a function at point x. Now you write down some remarks. You check here, if we have a function, this f of x, this is our point x is equal to a, x is equal to a. We know that this limit x tends to a negative means if we are approaching the values of a, this x to this a, but from this left, from this side, not greater than this a. At that time, if the value of the function is equal to the f of a, and if this condition purely, then we are saying that the function is continuous from left. ये जो function है ये left side से continuous है. And when we are giving the values of this x tending to a but greater than this a, at that time if limit x tends to a positive f of x, if it is equal to f of a, then we are saying that the function is continuous from the right. So for left we have this condition, for right we have this condition, and when these two are equal, then we are saying the function is continuous both left as well as right, and the function is continuous at that point. So here you write the remark. A function, the remark first. A function f of x is said to be left continuous at x is equal to a, is said to be left continuous at x is equal to a if and only if limit x tends to a negative, this f of x is equal to f of a. Similarly, a function f of x is said to be right continuous at x is equal to a if and only if limit x tends to a positive f of x is equal to f of a. So this is my, and now you write the C, but C third remark. A function, you see, a function is continuous at x is equal to a if and only if, now I have already written it, limit x tends to a, this left continuous equal to f of a, it is equal to right continuous. So this is your formula that you can apply if you have to check whether the function is continuous at the point or not. What you have to find out the limit from left and the limit from right, and after that you have to find out whether this is equal to f of a or not. I have already given you the method how we can find out this limit x tends to a negative of this left hand limit and how we can find the right hand limit. So these were the three remarks you have to keep in concentration. Now, going to our first definition, that was f of x is continuous at x is equal to a if f of a is defined, and if f of a exists. Second was if limit x tends to a, f of x exists. Third one was if limit x tends to a, f of x is equal to now f of a. These are the third conditions from the first definition. Now we will write the definition of discontinuity of a function at a point. You write a function. Now we have third condition is for a function to be continuous. If among these third conditions one or at least one condition is not satisfied, then at that time we cannot say that the function is continuous at that point. When the function is not continuous at that point, we say the function is discontinuous at that point. So a function is said to be discontinuous at x is equal to a if and only if and only first either f of a is not defined, if either f of a is not defined or if f of a does not exist. Second one, this was my first condition. The second one, the limit exists, but we say that a r b part if limit x tends to a, f of x does not exist, or c part if limit x tends to a, f of x exists. But third condition was if this exists, that must be equal to, for continuous, that must be equal to f of a. If this is now exists, but it is not equal to f of a. If the limit exists but is not equal to f of a, then we again say the function is not continuous. And the fourth one you write if limit x tends to a positive f of x and limit x tends to a positive f of x both exist but are not equal. If left hand limit is not equal to right hand limit equal, then the limit does not exist, and this is another. And fourth one you can write if this limit x tends to a negative or this one does not exist, then we say that the function is not continuous. That is the first one. So this is all about the continuity and discontinuity of a function at a point. Now we will define the last topic of continuity at continuity of a function, but we will define it over interval now. If we have an open interval a to b, open interval a to b, this is our a and this is our b, and if in this open interval a b, the we take any arbitrary point, for example this x, this c belongs to a to b. If at this point c belongs to this interval, the function is continuous, we will say that the function is continuous in this open interval. That in short means if the function is continuous in all the points that are between this a to b, but except this a and b, then the function is continuous. We say the function is continuous throughout the interval. So it is, we are taking here c arbitrary. This c can be any point that is between this a and b. So if the function is continuous at this point c, then we will say that the function is continuous throughout the interval. You write it. Continuous continuity of f of x is in an interval. Continuity of it. First we will define it on open interval. A function is said to be continuous in an open interval this a to b if and only if for all this c belongs to this open interval ab f of x is continuous. F of x is continuous. That means for all c belongs to a to b, if f of x minus f of c less than epsilon for all, this x belongs to c minus delta, c plus delta. This is our definition for continuity of a function in an open interval. Now we will define the continuity of a function over closed interval. This will be our last definition, and inshallah we will find out some special type of discontinuities tomorrow. So here this will be our last. Second one. Second, we will now define the continuity of function in a closed interval. In a closed interval, if we have this f of x, and if this is our a and this is our b, we say that the function is continuous over this interval a b, closed interval. But we know that in closed interval this a and b are also included. So first we will say that the function is continuous in this closed interval if the first condition is if the function is continuous over all the points that are between this a and b. So that means if the function is continuous in ओपन इंटरवल ए बी क्लोज के लिए पहले ये होनी चाहिए कि ये फंक्शन जो है ये ओपन इंटरवल में ए बी के ओपन इंटरवल में कंटिन्यूअस होनी चाहिए. तो we will write here first a function is said to be continuous in a closed interval a b if and only if first one is continuous if and only if limit x tends to a f of x is equal to f of a. Then we are saying that the function is continuous at this point x is equal to a. So we have to define the function is continuous here at x is equal to a. Then we say that the function is continuous in closed interval a b. But how we can, this x tends to a means we are giving the values of x very near to a, but from left as well as from right. But when we will give the values of this a from this left, from the left side, that means we are taking the values x less than this a. But the values that are less than x is equal to a, they are outside this interval a b. So we cannot say that this limit x tends to a from left a negative f of x. This limit means the limit when we are giving the values of x less than this a. But at these points, the this interval is not satisfied. Why? Because these values of x are outside this a to b. So this condition we have not to include. That means this limit x tends to a negative. This we cannot include in this interval. So what is then? Then the function must be continuous from the right. Right means when we are at that point, then we say that the function is continuous at this a. So that means limit x tends to a by f of x in a b. If this is then is equal to, that must be equal to what, beta? This f of a. And similarly, we cannot go beyond this a, so we cannot give the values of x greater than b. So second condition must be limit x tends to limit a negative. So that will from this side f of x, that must be equal to f of B. Then when these three conditions are getting satisfied, what? Positive function is continuous in open interval a b, and then the right hand limit of f of x is equal to at a is equal to f of a, and left hand limit of f of x is equal to f of b. Then we say that the function is continuous in closed interval. This is all about the continuity and discontinuity of a function at points and as well as an interval. Now tomorrow we will define the special types of discontinuities, and after that we will find out some functions that are discontinuous at some point. So this is enough today.